In the previous class, we were looking at the properties of uh, H of S, okay, of the entropy. And the last property we saw was extremal property or the upper bound. So we saw that whenever symbols are equiprobable, you are going to get the highest value for H of S or entropy of the source. So this is what we have seen, correct? Okay, let's move further. Okay, so the next property, this is property number 4. It is called as the additivity. This is also referred to as the split symbol entropy. So the statement goes in this way: if we split the symbol, right? Let's say the symbol is SQ. There is a particular symbol SQ, and it is divided into let's say small letter n, okay, number of sub symbols. Let's say the symbol itself is ABC or ABCD. Now you have options like you can split it into AB and C, so two symbols, okay, or ABCD can be divided into ABC and B, or ABCD, like that, or ABCD single, right, like that we can split it, right? So that's what we are talking about. Now we split the symbol into n sub symbols, all right, such that uh, okay, let's try to write it in this way. Okay, so such that SQ is equal to SQ1, SQ2, up to SQN. So there are n possibilities, so we have n such symbols, right? Again, whenever we split, we need some probabilities. Okay, so occurring with probabilities PQ1, PQ2, up to say PQN. Right, but whenever we talk about this kind of probability, the sum of the probabilities should be 1. So such that this basic condition needs to be met. That is, PQ is equal to PQ1, PQ2, PQ3, all the way till the PQN. That is also equal to, say, R is equal to 1 to n, all the n such symbols, you add all of them. So that is PQR. Sum of them is equal to PQ. Okay, now we have splitted the symbols. Let us try to calculate its entropy. Right, so then the entropy of the splitted symbols. How do you calculate? Let me call that as, say, H dash of S. Okay, it's a different H dash. Original symbol had its entropy H of S. Now I call H dash of S. Okay, so how do I calculate that? This should be equal to, originally I had, right, many symbols. I used to calculate them by using the P1, P2, P3, etc. Okay, now the qth symbol, I'm splitting that. Okay, so assume like this, we had symbols like S1, S2, S3 up to maybe SM. So in the middle, I had a symbol called SQ. This SQ is what I'm talking here. One symbol I split it, but other symbols, they are as, right, original, right? Still, we have not touched them, right? So they will be there. Is it okay? So in the sense, the entropy when I'm calculating now, H dash of S, that will be the H calculation with first symbol have probability P1, second symbol P2, okay, third symbol P3. In the somewhere in the middle, I'll get P Q minus 1. Till here, untouched. Okay. Now you see, I have a PQ coming into picture. This PQ is the one which we have splitted, right? Like this. Is it okay? So PQ is the one which we have splitted that up. Okay. Then I'm going to get the next term, that is P Q plus 1 dot 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 up to P Q N. All right. Now I understand that I have to use the following logic to do the calculation. First, let me try to write in this way. So that is equal to summation, say I is equal to 1. I'll do the calculation till Q minus 1. So till there we have no problem. This is Pi into log of 1 divided by Pi. Okay, that's the first term. So to this term itself, I'm trying to add the qith term, right? So that is plus summation. Let me write say r is equal to 1 to n, because that term has been splitted up, right? We have splitted the terms in this fashion, correct? So let me write it in this way. Okay, so let me make a small change in this. So instead of writing in this way, so the PQ itself I'll try to write. Okay, so let me write it in the this fashion. So PQ1, the Qth symbol, let's assume that we have split it, that Q1, Q2, Q3, Q4 up to PQN. That's how it has been split. Okay, right. Okay, now this makes more sense. Just to satisfy the equation, I made a change like this. Okay, so the equation says it is r is equal to 1 to n. So this is PQR log of 1 divided by PQR. Okay, so now let's try to make a small change here. This is summation I is equal to 1 to, let me make it q. If I want to add the qth term, I have to subtract the qth term. So see the change. I is equal to 1 to q. This is Pi log of 1 divided by Pi. So I added a qth term, so I should subtract the qth terms, right? So PQ log of 1 by PQ, then remaining terms as it is. Okay, so summation, say I is equal to 1 to n. This is PQI log of 1 by PQI, right? Fine. Now the PQ, what is PQ? PQ and this term is, right, it has to match, correct? Because PQ, I can try to write it as in terms of a PQI, because PQ is the one which we have splitted up, correct? So just see here, what is PQ? PQ is summation of, right, PQR, right? R is 1 to n. This, so I can replace, right? I can try to bring a summation over there, right? So I'll make a modification like this. So this is equal to summation I is equal to 1 to q. This is Pi log 1 divided by Pi minus, see PQ I'm trying to replace like this. I is equal to 1 to, it has been split into n pieces, right? PQI, but the log term as it is. This is log of 1 divided by PQ. Then remaining terms are there, that is I is equal to 1 to n PQI log 1 divided by p qi. Okay, now I can see that among the last two terms, we have a summation that is common. Let me try to take that common out, right, and see what happens. So this is equal to summation I is equal to 1 to q pi log 1 by pi. Then let me try to take a plus summation outside. Plus summation I is equal to 1 to n, and I'll also take pqi outside. So what remains inside when the pqi goes out? So this, okay, I can write this first. Log of 1 divided by pqi, that's the second term, minus the first term, log of 1 divided by pq. So we know that log a minus log b is log of a by b. Is it okay? Fine. So let's try to write in that fashion. Okay, so that means this is equal to summation I is equal to 1 to q pi log of 1 by pi plus let me try to write in this way. So summation, what is this term? If you can see, what is this term? Can I write it by some? Can I replace? I is equal to 1 to n pqi. I instead of I we have r. R is equal to 1 to n pqr is pq, correct? So I can try to write a pq over this. Okay, so this is nothing but the pq summation. I'm taking it out. Then you see I'll write the log of, so log a minus log b is log of a by b, right? So a by b is, this is a, this is b, so the denominator of the denominator goes to the numerator, so I will be writing a pq in the numerator, correct? So this is pq divided by pqi. All right, so the idea is this: on the left hand side I have the h dash of s, right? So h dash of s is a newly calculated entropy, okay, after splitting. So if I split a given term, right, I get the entropy called as h dash of s, right? But what is this? This is the entropy without splitting, correct? Look at yesterday's equations, right? So this is simply h of s, correct? Plus, you see, I'm getting, this is some positive constant. Why it is positive? Because log of anything can always be positive, and pq is a probability, so that's also has to be positive, right? So you see, this is, I can try to write a positive quantity plus, maybe I'll write a k here. So this k is some positive quantity. Are you okay? So what is the idea here? The one which we wanted to prove is h dash of s. Once you split, you get more probabilities coming into picture. More probability means more information. That's why entropy is more. Average information is more than the original h of s. So whenever you split, you get more information. Okay. So the point to remember, I'll write here. Okay. So I can write like partitioning of symbols partitioning of symbols into sub symbols can not decrease, okay, cannot decrease the entropy. It will be equal or more than that. Okay, fine. Then uh, that's the property number 4. And let's go for a term. Let's define a term, and this is called as the source efficiency, right? Source efficiency is denoted by eta, right, or eta s in some of the textbooks, doesn't matter. So that is defined as the entropy of a system divided by maximum entropy, okay, into 100. So we try to measure in percentage, that's why it's like this. So when we have what is called as an efficiency, we get the reverse of that. It's called as a redundancy, right? So I'll define that as well. So that is source. Okay, so source redundancy is R. Okay, R is already used, so R eta. So this is 1 minus eta s. Okay, so 1 minus the efficiency is the redundancy. Again, this will be a percentage if you write it as 100 minus that. Okay, if you write 1 minus eta, it will be a fraction, but we can definitely write it in terms of percentage as well. Okay, fine. Let's quickly go through some of the problems related to these topics. Okay, the first one, consider a system emitting the symbols A, B, and C with the probabilities 0.45, 0.35, and 0.2. Calculate the source redundancy. So in order to find a redundancy, we need efficiency first. For efficiency, we need the maximum entropy and the actual entropy. Correct? So let's start with the entropy of the system. That is h of s is equal to summation I is equal to 1 to 3. There are 3 different symbols. This is pi log to the base 2 of 1 by pi. So please calculate this. 0.45 log to the base 2, 1 divided by 0.45 plus 0.35 log to the base 2, 1 divided by 0.35 plus 0.2 log to the base 2, 1 divided by 0.2. So this gives 1.51, right? That's the amount of information per symbol, correct? Okay. So now we need h of s, the max possible value. If you see the concept we studied yesterday, this is simply log to the base 2 of the number of symbols q. Okay, in this case, 3 symbols we have. So simply you calculate log to the base 2 of 3 symbols. So we get a value equals to 1.58. Again, this is the maximum possible entropy. So bits per symbol. Right. Now we calculate the efficiency. So what is the equation? Efficiency is equal to HS by HS max. 1.51 by 1.58 into 100. Okay, so this comes to be approximately 95%. So you can calculate R eta is equal to 1 minus eta s. So that is 1 minus eta s for fractional case. Otherwise, this is 100 minus 95. Okay, so that is equal to 5%. Is it okay? Okay, normally this is one set of problem which we usually get to solve. Okay, other type problem we'll see later. Let's move further to the next topic itself. Okay, so that is called as extension of the zero memory source. A source extension is in general we call it as a source extension. Now, so let us assume that there is a source which emits two symbols, right? So two symbols may be S1 and S2. And whenever the symbols are known, we should also have a clear idea about what are their probabilities. Okay, say P1 and P2. Okay, so let's talk about the extension later. First, let's consider what we know already, right? So let me write what we know already. So consider a source emitting, say, two symbols. Two symbols, S1 and S2. Symbol 1 and symbol 2 with the probabilities defined as P1 and P2. Respectively. Right. So we know that since only two symbols are sent, the P1 plus P2 should be equal to how much? That should be equal to 1. And if at all I want to calculate the entropy, how we'll represent that is h of s is equal to, it's very simple, P1 log 1 by P1 plus P2 log 1 by P2. That's how we calculate. Now, so this whole source, let us say it is represented by S. Okay, this is sending only one symbol at a time, that is right, S1 or S2. Okay, now what I try to do, I'm trying to uh, so far we were considering like this, S1, then the next symbol emitted could be S1 once again, next symbol could be S2, then once again S2 or S1, then S2, then S2. Like this it is emitting the symbols. You are considering only one at a time. Okay, this is what we did so far. But now we introduce a concept called as extension. In the sense, instead of considering one, you consider two at a time. S1, S1, S2, S1, S2, S2, and so on. Are you okay? So if you try to consider, right, making a groups of two, then that is what is considered as the second order extension of the source. Okay, so that's what we are talking about, extension here. So anyway, so let me write that point, then we'll discuss further, right? Considering the second order extension of the source, right? Say source S, as we'll try to write that as S2, S square. So S square is the second order, right? So as S square, right? What are the possibilities you have? Since I have only two symbols, right? It is 2 to the power 2. What are the two? If I try to make the groups of two symbols at a time, what are the possibilities, right? We have four possible combinations. As S square, we can have four combinations, isn't it? We have four combinations. What are the combinations? S1, 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 S2, S2, S1, and S2, S2. So these are the four different cases. Okay, now how do you calculate the probabilities of each one of them? Okay, so I can try to write in this way. The probability of getting S1, S1 should be equal to, now we already have discussed one point in our previous session, that emitting of my current symbol has nothing to do with the what are the past symbols, right? So statistically independent. There is another word for that. It is memoryless. There is no memory. What was the previous emission? The system or the machine does not remember that. There is a memoryless. This is called as a memorylessness. Are you okay? So this particular system is memoryless, or the symbols emitted are statistically independent. So independent from probabilities and right, the concepts related to probability, recall that if you have two events, now the two events are emitting S1 followed by another S1, right? If two events are independent, then the overall probability of both events occurring one after the other is simply probability of S1 into probability of S1. Are you okay? So that is nothing but it's P1 times P1. So that I can write it as P1 squared. Similarly, let's calculate the other three. S1, S2. This should be calculated as probability of S1 into the probability of S2. So that is P1 into P2. That's all. Okay. P1, P2. Probability of S2, S1 is equal to probability of S2, probability of S1. So that is once again P2, P1 or P1, P2, doesn't matter. And the last one is probability of S2, S2 is probability of S2 into probability of S2. So that is P2 into P2 squared, right? So these are the probabilities. Are you okay? Right. Now let us try to calculate the entropy of the second order extension. Right. Therefore, entropy of the second order extension. That is, we try to denote that as h of s square. H of s square is equal to how many possibilities? We have 4 possibilities. So I is equal to 1 to 4, right? Write the same thing. Pk into log to the base 2 of 1 by pk. Okay, so let's try to expand them. So the first set of symbols are S1, S1. We know that their probabilities are P1 square log to the base 2, 1 divided by P1 square, plus the second symbol is P1, it's S1, S2. So probability is P1, P2 into log to the base 2, 1 divided by P1, P2. Is it okay? Plus the next set is once again P2, P1 log to the base 2, 1 divided by P2, P1. And the last term is P2 square log to the base 2, 1 divided by P2, P1. Is it P2, P1? Sorry, my mistake. It's a P2 square, right? Let me just correct that. So this is P2 square. Okay, so let me try to make, is it possible to make any changes? Yeah. So what I do here, see there is a square term here. I can take the square term outside, right? By multiplying. So it's like 1 by P1 whole square. The square can be brought out as 2 times. So 2 times, this is P1 square log to the base 2 of 1 by P1. Are you okay with the first term? So second term, it's repeated. Second and the third terms are same. So I can write once again 2 times P1 P2 log to the base 2, 1 divided by P1 P2. And the last term has P2 square log to the base 2 of 1 by P2 whole square. So the whole square, I'll try to remove it by making it as 2 times. Okay, 2 times P2 square log to the base 2, 1 by P2. In the next step, what we can do, let's try to look at the term containing the P2, and okay, let me try to write in this way. So what I try to do here is, so let me write the first term as it is. I have not changed this. This is 2 times P1 square log of 1 by P1. Then look at the second term, right? The second term, I will split it in this way. Okay, that is 2 times P1 P2 log of 1 by P1 only I'll write. So what should be the next term? That's also 2 times P1 P2 log of 1 by P2. Because this should look like log of AB. Log AB is log A plus log B. Okay, so there is a 2 P1 P2 that gets multiplied to both A and B. Okay, so that's how I am writing that. Plus the last term as it is. Plus 2 times P2 square log to the base 2 of 1 by P2. Okay, now 2 P1 P2, anyway I am that. Can I try to take something common so that we can try to write a common term? Okay, so in from the first, okay, so from the first, let me take out 2p1 outside. Okay, 2p1 times log of 1 by p1, I'll try to take it. Okay, 2p1 log of 1 by p1. This is what I'm trying to take out from the first two terms. So what remains here, first term gives me a p1. Second term, 2p1 log p1 has been moved out. It's a common term, so I'm left with p2. Let's try to do the same thing from the the third and the fourth term. I'm trying to take out 2 p2 log of 1 by p2. Let me try to take this out. So what remains here, since 2p2 has gone out, I'm left with the p1 in the third term, and the last term will give me a p2. Is it okay? All right. So now what is this value? P1 plus p2 equal to 1, right? So p1 plus p2 equal to 1. So I'm not writing that, right? So in the next step, I'm writing this as 2 times. Yeah, so 2 is out. When 2 goes out, 2 is common. I'm writing p1 log of 1 by p1 plus p2 log 1 by p2. I know that, right? 2 times whatever is inside the bracket is h of s. So I am calculating h of s squared, right? So this is the meaning. So h of s square will be 2 times h of s, right? Similarly, we can also prove, h of s cube will be 3 times the h of s. So already you know the h of s, simply multiply by 3 to get the answer, right? H of the fourth extension will be 4 times h of s and so on. So in general, we can definitely write h of s to the power n, nth extension is going to give you n times h of s as the answer. So nth extension will definitely generate this as the answer. Is it okay? Fine. All right. Let's go to a problem based on this concept. A source emits 3 symbols S1, S2, S3 with probabilities 1 by 2, 1 by 4, and 1 by 4, right? Show that h of s square is equal to 2 times h of s. So we have to prove it. So what we do, first we directly calculate h of s, right? H of s is equal to summation I is equal to 1 to 3. This is pi log to the base 2 1 by pi. So simply it is 1 by 2 log 2 plus 2 times 1 by 4 log 4. Okay, that will be the entry. So this is equal to 1.5 bits per symbol. Right, that is h of s. Right, now we already know that h of s square, if we want, somebody asks us to calculate, simply I do 2 into h of s, but now that is not a question. Do the extension, calculate its entropy, and show that h of s square is equal to 2 into h of s. That's what is the question. So we need to do the extension. All right. So what are the possibilities? Now there are, right, how many symbols? 3 symbols, correct? So the second extension implies there will be 3 to the power 2 number of symbols. Okay, this is how you calculate. So 3 square is 9. I have 9 different possibilities. Okay, so let's calculate, right? So probability of 1 by 1, let's write. So S1 is 1 combination, correct? So that is probability of S1 is probability of S1 half into the S1. So that is 1 by 4. Is it okay? Like that. You calculate every possibility. S1 and S2 might come. So that is 1 by 2 to 1 by 4, 1 by 8. Okay. Next, S1, S3. Right? S1 into S, probability of S1 half. This is 1 by 4. That's 1 by 8. Similarly, do the calculation for all the possibilities, right? P of, next I might have S2 followed by S1. 1 by 4, 1 by 2, 1 by 8. Then probability of S2 followed by S2. 1 by 4 into 1 by 4. That is 1 by 16. Right? Then probability S2, S3. Probability of S2 is 1 by 4. S3 is also 1 by 4. That is 1 by 16. Are you okay with this? Let's proceed. So then I may have P of S3, S1. Probability of S3 is 1 by 4. S1 is 1 by 2. That is 1 by 8. Then probability S3, S2. S3 is 1 by 4. S2 is 1 by 4 by 16. And last set will be S3, S3. So what will be that? That is also 1 by 4 into 1 by 4. So you have 1 by 16. So second extension will be showing the following symbols and those probabilities which we have calculated. Is it okay? So let us write the, therefore, h of s square. Right? How many terms I have? I have 9 terms. So I is equal to 1 to 9. So this is not q. This is 1 to 9. You have total 9 terms. Individual probability is into log to the base 2 of 1 by pi. But I can see that many terms are repeating, so I can club them all together. Okay, so the 1 by 4 happens only one time, only once. So I can write that as this is equal to 1 by 4 log to the base 2 of 4. That is the corresponding to first term. Then I can check how many 1 by 8s I have. 1, 2, 3, 4 times. So 4 times 1 by 8 log to the base 2 8 plus how many 16s we have? 1, 2, 3, 4, right? So 4 times 1 by 16 log to the base 2 16. Okay, please calculate this. This is equal to 3 bits per symbol. So now what we know is this, right? That is h of s square is equal to 3, which is 2 into 1.5. So that is 2 times h of s. Hence, whatever they have asked, we have proved it. Okay, so that is the concept of extension of the memory sources. So in this case, we have considered the memory sources to be, the information sources to be memoryless. They are not remembering what they had produced previously. Okay, so that's the concept.